In 4.1, we'll look at the beginning of the apportionment problem. Kind of like in 1.1 for voting, they don't give you the method of what to do until the next section, but this one is the tools about how to get started on the method. Okay, so, and they give you a little history part of this, but at the Constitutional Convention for the United States of America, they were one of the most important or most heated debates was how to spread out the representatives. So obviously we know now what they decided on was the House, which is dependent on the population of each state, and then the Senate, where everybody gets 2 seats. But namely, the small states wanted all states to have the same number of representatives. The larger states wanted some kind of proportional. They were like, well, if I have 5 times as many people, shouldn't I get 5 times as much say? So the compromise was what we have now, the Senate and the House. So while the Constitution makes it clear that the seats in the House are allocated based on the populations, according to their respective numbers, is what it says. It doesn't say exactly how to do that. So they probably figured that was a minor detail and a little bit of arithmetic. They could agree upon it. What they didn't know is they were setting themselves up for the apportionment problem. How can you actually do this fairly? And so they, because they just said, according to their respective numbers. So we'll look at a scenario or a couple scenarios and see why that might not be as easy as it sounds all the time. So 2 things that make this apportionment. You're dividing and assigning things, and then you're doing this on a proportional basis. So in the terms of the representatives, more seats or more population gets you more seats. Twice as much population should get you roughly twice as many seats if it's going to be proportional. So proportional and some kind of organized thing. We can't just guess, who should get however many seats. Okay, so here's an example where we'll look at how this can start to become a problem. And 4.2, we'll figure out one of the solutions. 4.2 is Hamilton's method. So mom has a total of 50 identical pieces of candy. So some random person, and she's planning to divide them amongst 5 kids. So if we were just going to divide them evenly, everybody gets 10 pieces of candy, right? But also she wants to teach them about work ethic, or maybe get some chores done. So she's going to do however many minutes they work corresponds to how much candy they get. So if somebody doesn't do any chores that week, then they don't get any candy. So here, she kept an up-to-the-minute record of how much work everybody did at her kids A, B, C, D, E. And it adds up to 900 minutes of work got done total between them all. You can see that looks like Ellie did the most, then Doug, then Connie, then Alan, then Betty. I would assume they're different ages too. So they all did different amounts of work. So now if we're going to say, well, what fraction of the candy do they all get? It'd be nice to know what fraction of the amount of work they did. So I can say, okay, like for example, we'll look at Alan. So Alan worked for 150 minutes, but that's out of a total pie of 900. So 150 divided by 900 gives you 0.1666. It's repeating, but all right, so how can I decide how much candy he did? Well, he did about, if we want to look at that as a percentage, he did about 16% of the work. Or 6, 7, if there's another 6, it would technically round up. So he did about 16% of the work, so he should get about 16% of the candy. If we look back, there were 50 pieces of candy. So if I want to know what is 16% of 50, I can do 16% times 50. And so 16.6 repeating times 50 is 8.33 repeating. All right, so he did 16% of the work. 16% of the candy is 8.33 pieces. So here's where the dilemma starts. Should we give him 8 pieces or 9? I'm sure he would argue for 9, but if we round up in everybody's case, we'll probably run out of pieces of candy and give away more than the 50 that we have. But then he is getting gypped by a third of a piece. I think they said they're caramels or something, so they're trying to make it where they're not easy to cut into halves. Or if I think of this like the representatives problem, definitely can't have a third of a representative. And so here's where we start to be able to decide, well, what should we do? So this is kind of the heart of the apportionment problem, is what happens when it doesn't come out to a perfectly nice even number. So here's where they got the 8 1/3. He did 150 out of 900 minutes of work, and we multiply that by 8 1/3 because that's what fraction of work he did. So should he get 8 or should he get 9 pieces of candy? So similar when we do the rest of those, their portion of work, Betty gets 4 1/3 pieces, Connie gets 9 11/18. Also, when you're doing this, I don't care if you use fractions or decimals. You'll see when we actually get to Hamilton's method, decimals might be a little easier because fractions, you need common denominators to accurately compare which fraction is bigger. So you might want to go with decimals, but it's totally up to you. Doug should get 11 1/3 and Ellie should get 16 7/8. So none of these amounts can happen. So when should we round up? Should we round down? What should we do? So there's the heart of the reason that there's an apportionment problem. Okay, so all the things is that we have the extra doesn't divide in evenly, and so you can see the issues. We won't get the full one of the full solutions until 4.2. All right, then they want to look at another one, which is in year 2525, all the planets of some galaxy have signed a treaty and they're going to be ruled by 50 elders according to their populations. And so then if we look at the population, this one's got 150 million people, this one has 78 million people, this one has 173, total of 900 billion people. If you notice something about the numbers for this, it's the exact same problem. These are all the same minutes as the kids with the candies. I think one thing they're just trying to point out here is the candy, maybe you could round them all down and keep the extra candy for yourself or something. But when the stakes start to get high for apportionment, that one person could make a difference in your voting, then it starts to become even more of a problem because the stakes are high. So what do I do with those extra representatives? Okay, so two things they're going to point out in here, and they're just saying the same thing I just said about the two problems are the same. They have the same numbers. They just changed the scenario. Okay, and so they're going to show you a faster way than figuring out what percent of the work everybody did. How can I start to figure out about how many seats should everybody get? So in this one, there's 250 seats in the Congress, and then we'll get the populations of all these states. So this one, 1.6 million, this one's 6 million, 150,000, 2 million, 685,000, 988,000, so 2.5 million people total. Okay, so the first thing we're going to talk about here is what's called the standard divisor. So the standard divisor is the total population divided by the number of seats you have to give away. Put a big division in there. All right, so the total population divided by the number of seats you have to give away gives you 50,000. So think about what this means is if there's 12 million-ish people in this whole population, and we only have 250 seats to get away, so how many times does 250 go into this? This 50,000 is saying this is how many people it takes to get a seat, right? So if this is the total number of people, we said how many times do the seats fit into that? So if you have 50,000 people in your population, that should correspond to about one seat. So notice even I could just kind of eyeball, this one has 150,000 people, so they should get 3-ish seats. They're a little more than 150, right? And so what they're saying is the standard divisor is how much of the total population you need to get a seat. Okay, so now that we have a yardstick, we can decide, okay, 50,000 people corresponds to getting a seat. Then if you just divide 50,000 into all the populations, so say that first one was 1.6 million-ish, that means that 50,000 goes in there 32 times. So that means they should get about 32 seats. So that's how you find the standard quota. So they're just trying to do the same thing we did with the candy, but faster. If you find the standard divisor, you divide that number into all the populations to get the standard quota. So you have one kind of thing to measure it against. It just makes the calculations quicker. So obviously you can't get 32.92 seats. So should they get 32 or should they get 33? And so that's the thing that we'll figure out in 4.2, how to do that fairly. But to begin with, in this one, all you want is the standard divisor and the standard quota. So just getting you ready for 4.2. So standard divisor is the total, this divided by this. And then the standard quotas come from, once you figure out that the standard divisor is 50,000, so the 12.5 million divided by the number of seats you have to give away. So every 50,000 people in your population, you get a seat. So you say, well, how many times does 50,000 go into this number? How many times does 50,000 go into this number? How many times does 50,000 go into this number? This was that one that we said is kind of easier to eyeball, just over 3 times, because that's 50, 50, 50 to make 150-ish. So everybody should get about these many seats. To figure out how to make them all whole numbers is what we do in 4.2. But in 4.1, they'll just have you figure out the standard divisor and the standard quota. So, same thing. Also, if you're thinking, well, why don't we just use the normal rounding rules? If it's higher than 0.5, we'll round up. You can have scenarios. So here's one. If you round all the ones that were above 0.5 up, see how you give away an extra seat? So that doesn't always work either. And so that's why we have to come up with some kind of method to be able to do that fairly. So we can't always round down, we can't always round up, we can't even use the normal 0.5, because if we have too many of them that are just over 0.5, we can end up giving away too many seats. So this is the same thing we just said. And then just to wrap up, the things that are important are the states. So they could be the kids that are getting the candy, whatever we're spreading something out to is the states. The seats are how many identical indivisible objects are being divided. So they could be pieces of candy, they could be representatives. It's just how many things are getting spread out between everybody. And then the populations, so say for the kids, it was how many minutes of work they did. For those states or galaxies we just had, it was their literal populations. But so each one has their own population, and the total population is, well, what if I add those all together? And so then the only two things that you'll be computing, the important parts here, are the standard divisor and the standard quota. So standard divisor is one number that's the same for the whole problem. It's the total population divided by the number of seats you have to give away. So that tells you how much population or how many you need to get a seat. And then the standard quota is each of the populations divided by the standard divisor. So you go down your whole list and you do population divided by standard divisor for the first one, the second one, the third one, all the way down. And then the lower quota, so picture like this one where they got 32.92. On the lower end, they might only get 32 seats. On the upper end, they might get as many as 33 seats. So that's called the lower and upper quota. They won't go outside of that, but it depends how they round up or how they round down. So what we want is something that will give something that's proportional and will always produce a fair apportionment. So if you did the same method, say over and over, you'd get the same one. And so 4.2, we get to look at the actual method. But in 4.1, they just have you practice the standard quota, standard divisor, so that when you get to 4.2, you've already got that part of it down.